It consists of a vertical member and an inclined member with points A, B, and C. There's a pin connection at A. At the support C, there is a roller connection, and then B is fixed at this joint. The first step to solving this problem is we want to find the external forces. First, we need to designate our dimensions to this problem, and that requires a general assumption in the beginning. So here we're going to assume that this dimension is 2 feet. From there we know that we have a dimension of 5 feet to this center point on the vertical member, 7 feet to the midpoint at B, and then going across the inclined member, we're going to have 7 feet, another 7 feet. From there we can determine that half of the distributed load acting on the roof member will go on to both endpoints. So we're going to multiply our 300 pounds per foot of the distributed load by 3.5 and 3.5 at the two endpoints, and then at the middle it's going to take half of both of these center members. So we're going to multiply 300 pounds per foot by 7 feet. Down here we're going to multiply our 500 pounds per foot by 1 foot to get our point load at this center point at A, and then we're going to multiply 500 by 3.5 here, and then 500 by 6 feet at this midpoint, and then another 500 multiplied by 3.5 feet at the point at B. Now that we've determined our point loads, we now need to determine the forces AY, AX, and CX, because the ultimate goal is to be able to draw our shear and moment diagrams. So if you follow me over to our equilibrium equations. So in order to sum moments about A all equaling to 0, we need to recognize any forces in the X and Y direction. Obviously, in this inclined member, we need to derive those X and Y forces. Along the vertical member, we won't have any of the vertical forces. We won't have any forces in the Y direction. We have all of these forces acting in the X direction. So then they are simply computed based on their distance from A. Computing the forces in the X and Y direction based on the angle 30 along this inclined member, we can then sum those individual components in their own X and Y direction based on their distance from A. And through our summation of moments about A, we can determine that the force in the X direction at the point C is negative 5,133 pounds. Moving on to our sum of forces in the X and Y, we can solve and find that our force in the X direction at A is negative 3,967 pounds, and our force in the Y direction at A is 3,637 pounds.
Now that the reaction forces for member AB of our beam have been found, we can rotate that beam 90 degrees clockwise and find our first shear and moment diagram for beam AB. So, using the graphical method of analysis, we start with our shear diagram. So starting at point A, we have 3,967 pounds in the vertical direction, 500 in the negative direction. So, that sum is 3,467 pounds, which is our initial shear at point A. Moving over 2 feet, we go down a magnitude of 500 times 3.5 pounds, resulting in 1,717 pounds, 2 feet from A. Moving over again 5 feet, we go down another 500 times 6 pounds, resulting in negative 1,288 pounds. Again, moving over 7 feet, we go down another 500 times 3.5 pounds, resulting in negative 3,032 pounds. So now that the shear diagram has been found, we can find our moment diagram. By definition, the moment diagram is found by finding the area under the shear diagram. So, our initial shear is 3,467 pounds. Multiplying by 2 feet over, we find that the first value of moment is 6,934 pounds. Again, adding in the area under the shear diagram between 2 feet over and 7 feet over from point A, we take 17 pounds multiplied by 5 feet and add it to our initial 6,934 to find our second point of moment at 15,519. Adding in the negative 1,288 times 7 feet to our value of 15,519, we result in a final moment value of 6,500.
The third and final part of this problem deals with the shear and bending moment diagram for member BC. Find our starting shear value first to start this part of the problem. We take a free body diagram right after the joint at B to find our starting shear. This can be done by summing the forces in X and Y and adding into those equations an unknown shear force and an unknown normal force right at the joint. After doing those equations, we found that the starting shear of our second diagram is going to be 583 pounds. Now after this, you do the shear and moment diagram just exactly the same way as you did for your first member. So we follow it over until we reach this point load here, going down 300 times 7 to a value of negative 1517. We go over and we add our resulting force here. We're ending at a force of 0. Our moment diagram is exactly the same as what Mitch just described, except for this time we're going to start over at 0 because we know that the moment is 0 at this connection. If we take this area, negative 1517 times 7, we will get the resulting moment here. That is 10,619. Now this we would take away from the moment diagram, so it's 583 times 7, which is a value, taking away from this value is a value of 6,500. Now a good check to make sure that you've done this correctly is that your moments should be equal in the center. So if we look at both diagrams, this diagram has an ending moment of 6,500, and this diagram also has a moment of 6,500, meaning that we've done the diagram correctly. Structuralysis. Structuralysis. Structuralysis.